Hello friends, welcome to session 10. In this session, we will cover the probably approximately correct theory or the PAC theory, and we will also cover what is known as the generalization bound. Let's get started. Okay, a quick recap as we have always done of the framework that we are using for studying the theory of learning. There is a target function which we denote by the letter F that maps every point in the input space X to a point in the output space Y. So for any given input Xi, you have an output Yi, and this target function is called such because it is the function that we want to determine. Okay, so this is the function that we want to find out what that function is, and we have denoted it by the letter F. We said that the inputs Xi are governed by a probability distribution P, and the same probability distribution also governs the choice of our training samples. We have n training samples in all. We also defined the idea of a hypothesis set, and the hypothesis set H essentially contained all possible hypotheses, and there could be an infinitely many of them. The job of the learning algorithm is to select a hypothesis from the hypothesis set based on the training samples such that the selected hypothesis replicates the target function f as closely as possible. To define this idea a little bit more mathematically, we defined two more quantities. We defined a quantity En, which is the in-sample error, and the in-sample error is defined for any hypothesis. Okay, so for a hypothesis H, the in-sample error EIN is basically the ratio of the number of points where the output of the selected hypothesis does not match the output of the target function, right? So essentially this is the number of mistakes that the selected hypothesis makes on the training data. That's the in-sample error for that hypothesis. We also defined a Eout. Eout is the out of sample error, and it's a probability because it deals with inputs that have not been seen so far. In other words, they are not a part of the training samples. And Eout is the probability that the output of the selected hypothesis does not match the output of the target function, right? The job of the learning algorithm, as we said, was to find the best hypothesis, which we denote by the letter G. Find the best hypothesis, also called the final hypothesis, G, and G is such that it minimizes E out. Okay, so E out, which is the probability of the error on unseen samples as well, not just on the training examples. That would be our final hypothesis. The final hypothesis G is the one that minimizes E out, and the job of the learning algorithm is to determine this G from the hypothesis set H. So this is the framework that we have been dealing with. So as we said, our task has always been to minimize E out, minimize the out of sample error. And if we want to minimize E out, we will need to understand what E out actually is. And one way to understand E out is to decompose it into components. So the idea is, if we can understand what goes into E out, we can possibly deal with those individual components and try to minimize them. That is the logic. So therefore, we want to decompose E out into its components. A logical question to ask would be, is it possible to relate E out to E in? For example, is it possible to express E out as equal to E in plus some quantity? And why would you ask this question? I mean, if this was possible, you could then focus on minimizing this additional quantity in order to make E out be equal to E in as much as possible. So therefore, this is a valid question to ask. We've looked at a number of situations in the prior two lectures, and here is what we know about possibly correlating E out and E in. So let me ask a series of questions. The first question is it possible to ensure that E out is equal to E in? Well, in the general sense, the answer would clearly be a no, right? Because it is not possible to ensure that E out is always equal to E in. Is it possible to ensure that E out is always within a margin from E in? In the sense, is it possible to ensure that the absolute difference between E out and E in is always less than a quantity that you can specify, let's say epsilon? And the answer to that question is also a no. If this was your E in, for example, it's not possible to guarantee that E out would always lie within a certain margin from E in. That's not always possible. Next question. Is it possible to ensure that the probability of E out being equal to E in is higher than a threshold? Okay, now we have introduced probability here. Why did we introduce probability? Because in general we know that a lot of doors open if you start thinking in terms of probability rather than thinking in terms of absolutes. Okay, so a lot more becomes possible if you start dealing with probabilities, and therefore we've introduced probability, and we are asking the question, is it possible to ensure that the probability of E out being exactly equal to E in is higher than, say, a given threshold? And the answer to this question is again a no. Next question, sort of a combination of the previous questions. Is it possible to ensure that probability of E out minus E in being greater than a given quantity epsilon is lower than a threshold? Okay, so what is this question saying? This question is saying, is it possible to ensure that, let's say, if this is E in, is it possible to ensure that the probability of E out lying within a small band around E in is greater than a threshold, or the probability of it lying outside this band is lower than a threshold? Is that possible? And it turns out that under certain conditions, the answer to this question can be a yes. Okay, the answer to this question can be a yes. So you can actually make probability of E out minus E in absolute greater than epsilon lower than a threshold. This is possible under certain situations, and this is the underlying idea. This is the idea underlying the PAC theory. Now, because this idea is so important, I want to move on to an analogy. Okay, let's understand this with an analogy. Set P probability of absolute E out minus E in greater than epsilon lower than a threshold. Okay, and let me explain this idea with an example of estimating marks in a final exam based on marks in a practice exam. So, for example, let us assume that you've been coaching your cousin for his 10th standard exam or whatever exam, and you gave him a practice examination. Okay, and you were asked by your relatives to estimate the marks that your cousin would get in the final exam based on the marks he got in his practice exam. Let us say he got, I am just selecting a number, 86.478. Okay, in his practice exam. This is his score in the practice exam. I have given it to 3 points of decimal because I want to sort of mimic a situation where those marks in the practice exam and marks in the final exam could assume it could be any real number, and therefore, just assume that there are so many questions that this kind of a any real number is possible. So let's say these are the marks that your cousin got in his practice exam. The question to ask is it possible to guarantee that he will get exactly these marks in his final exam? And the answer to that question is obviously a no. I am going over the questions that we asked in the previous slide. Is it possible for you to guarantee that that your cousin will get marks in the final exam lying in a small band around 83.478. This small band, the value, the size of this interval will be specified by somebody else. That's the epsilon in this equation. But is it possible for you to guarantee with 100% surety that his final exam marks will be in this range? And the answer to that question is obviously a no, because he may have a bad day and end up somewhere over here, right? Is it possible for you to ensure, third question, is it possible for you to ensure that he will get exactly 83.478 in his final exam? And the answer to that question again is a no, because this is a real number and the marks in the final exam could, vary, and they could take on any real number, and ensuring that he gets exactly 83.478 with any degree of certainty, it's impossible. So the answer to that question was also a no. The last question we asked is it possible for you to say that the marks he gets in the final exam will lie in a certain interval around 83.478 with some probability? Is it possible for you to guarantee that? And in certain conditions, yes. The answer to that question is yes. You could possibly guarantee under certain situations that if he got 83.478 in his practice exam, the probability that his marks would lie in a particular band could possibly be said to be greater than a certain threshold. Okay. Or you could ensure that the probability of his final exam marks lying outside this band is lower than a given threshold. You could possibly ensure that. So this is possible, and this is the idea underlying the PAC theory. This is the mental framework underlying the PAC theory. Okay. Okay. So let's sort of codify what the PAC framework is. The PAC framework says that you need to be able to ensure that probability of the absolute difference between E out and E in being greater than a given quantity epsilon is less than a delta. Okay, here E in is of course the in sample error which we talked about. E out is the out of sample error. Epsilon is called the approximation error. It is called the approximation error because it tells you how close E out and E in will be, or will likely to be. So this is called the approximation error, and 1 minus delta is the confidence. Okay, 1 minus delta is the confidence. So essentially what you are saying here, the probably approximately correct framework in the PAC framework, what you say is that the probability of the absolute difference between E out and E in being greater than a given epsilon should be less than or equal to delta. Okay. Learning is said to be possible when delta can be made arbitrarily small for a given epsilon. So why would you like to make delta arbitrarily small? Because you would like to make 1 minus delta, the confidence, as high as possible. You would like to ensure that with a very low probability, the absolute difference between E out and E in is greater than your given epsilon. Okay. So again, I'm going to draw this on a line. If this is your E in, let us say this is epsilon on both sides, this is epsilon, this is epsilon. What you want to ensure is that you want to ensure that the probability of E out lying here or here is less than delta, and you would like to make delta as small as possible. That means with higher and higher probability, you want to ensure that E out remains in this region for a given epsilon, and if you can do it with arbitrarily high probabilities, you will say that learning is possible. Okay, so this is the PAC framework that we are going to deal with. Okay, so mentally we understand what we are trying to do. It seems fairly logical. Like I showed in the example dealing with marks in the final exam, it is something that it's sort of a logic that makes sense to us even in day-to-day lives. So where do we go from here? We've said that if you can make delta arbitrarily small, you will declare that learning is possible. And therefore, estimating delta becomes important, right? So what is really delta? Well, you could say at the outset that you can imagine that delta depends on certain quantities that are in your control, right? I mean, the first is of course the approximation error which you specify. You specify epsilon, and you can imagine that delta is a function of epsilon. So for example, if your cousin got 83% in his practice exam, you could say with relatively low probability that he will get more than, let's say, 82 in his final exam. But you could say with a very high probability that he will get more than 50% in his final exam if he has got 83 in his practice exam, right? So the band that you permit, the approximation error that you permit, of course, is going to determine the probability of your guess, right? So delta is going to depend on epsilon, and that makes sense. Delta is also going to depend upon the number of training samples. So for example, how exhaustive was your practice test, or how many training samples were chosen? It seems fairly logical to assume that as the number of your training samples increases, your delta would decrease, right? Because more training samples means you have a better handle on your target function. So it makes sense that delta would depend on n. And finally, delta would also depend upon the hypothesis set, right? I mean, the sort of hypotheses that you have in your hypothesis set would determine the behavior of delta, or that would be an attribute that would contribute to delta. So we understand, or we imagine, that delta would be based on these parameters, and the rest of the lecture is going to focus on finding out what delta is. Okay, so that is what the rest of the lecture is going to be about. Now there is a probability here, and therefore it makes sense to ask the question, probability based on what? I mean, what is the random variable here? And the answer is obvious. The answer is simply the data set used for training. So the data set that you are given for training samples, I'm speaking about the training samples, the training data that you have been given could be selected in numerous ways, in infinite ways, and that is the random variable that gives rise to this probability. That is why we have a probability here. There is a certain dependency on the actual data set that you use for training, right? Now, like I said, the rest of the lecture is devoted to finding the value of delta and the conditions under which it can be made as small as you like. Okay, so that is the goal of the remainder of the lecture. And this journey is going to be a very interesting journey. It's going to be an interesting journey because it's going to involve some interesting twists and turns. Some very interesting logical arguments are going to be made, and therefore it's going to be fun understanding how you come up with the value of delta. Okay, so that's what the rest of this lecture is going to be about. Okay. The starting point for our journey is going to lie in probability theory. And one thing that we use often from probability theory is the idea of sampling based estimation. What is sampling based estimation? Consider the scenario where newspapers and media houses conduct opinion polls prior to elections, right? So they ask a small subset of people who they are going to vote for, and based upon what people in that small sample say, they predict the behavior of the entire population and predict the result of the elections. So this is one example of sampling based estimation. Another example is market surveys for products. Now many companies often conduct market surveys for their products. They ask a small target group of people what they think about a particular product, and judging based on those answers, they decide how the product is going to fare in the general population. So again, this is an example of sampling based estimation. A third example could be quality analysis. Let's say you are a manufacturer of shirts and you manufacture maybe many thousands of shirts a day. It is impossible for you to analyze the quality of each individual shirt, and therefore what you do is you pick a small sample from your daily batch, evaluate the quality of that small sample, and based on the quality of that small sample you make a judgment about the quality of the entire batch of the day. Okay, so this is also an example of sampling based estimation. We are perfectly comfortable with these ideas in our day-to-day life, but the question is, do these have any specific theoretical basis? So let's ask the question, does the idea of sampling based estimation have any theoretical grounding at all? And it turns out that they do. I mean, they have a basis in what is known as laws of large numbers, which are certain laws in probability theory. Okay, so this is going to be our starting point, and we are going to begin with one law of large numbers, which is called the Hoeffding's inequality. Okay, so let us see what the Hoeffding's inequality is. Consider a bin with marbles of two different colors, red and green. This is a bin that is of very large size, potentially infinite size, okay, and it has an infinite number of red and green marbles. You randomly draw n marbles from this bin. Okay, these are n randomly drawn marbles from this very large bin of red and green marbles. I'm going to define certain quantities. We define mu as the bin frequency. It's called the bin frequency, and it is simply the probability of getting a red marble from the bin. So if you picked a random marble from this bin, mu is the probability of that random marble being a red colored marble. Nu is the sample frequency. Okay, nu is the sample frequency, and it is the ratio of red marbles in the n drawn marbles. So you had these n drawn marbles, and nu is simply the ratio of the number of red marbles in this sample, right? So now instinctively you will assume that mu will be close to nu, right? Because these marbles are drawn from this big bin, you will assume that mu will be close to nu, and your intuition would also suggest that mu would get closer and closer to nu as n increases. So as you draw more and more marbles, your sample frequency would start approaching your bin frequency. Okay, that is essentially what the Hoeffding's inequality says, but it quantifies this difference between mu and nu. The Hoeffding's inequality is a probabilistic statement, and it says that the probability of the absolute difference between mu and nu, being greater than a given quantity epsilon, is going to be less than this number, 2 times e to the power minus 2 epsilon square n. Okay, now what you imagined is borne out in this equation. As n increases, this quantity is going to decrease. As n increases, this quantity is going to decrease, which means with the probability of mu deviating from nu is going to go lower and lower, right? So mu and nu are going to come close to each other as n increases. Epsilon is under your control. Okay, so you can define epsilon. This is the Hoeffding's inequality. What can you say about this inequality? Firstly, what you can say is that it applies for all ratios of colors. So this inequality is independent of how many red and green marbles are there in this bin. It applies for all bins that have any ratio of green and red marbles. It is valid for all n. So it holds irrespective of the number of marbles you draw from the bin. Okay, valid for all n. It is valid for all epsilon. This Hoeffding's inequality holds irrespective of the value of epsilon you choose. Epsilon is a number that you choose. You would typically choose a small number. Depending upon how severe you want to be, you could make it smaller and smaller. But epsilon is under your control. And this inequality holds for all epsilon. I mean, epsilon is there on both sides of this equation. And finally, there is a trade-off between n and epsilon, right? So if you increase epsilon, you can reduce n for the same probability bound and vice versa. Okay. So let me take a few numerical examples just to make this point. If I choose epsilon equal to 0.25 and if I specify that the probability should be less than 0.3, in other words, this thing should be less than 0.3, you get n equal to 15. So if you equate this to 0.3 and substitute epsilon equal to 0.25, you get n equal to 15. Okay. For epsilon, if you tighten epsilon a little bit more, epsilon equal to 0.02, and if you specify that the probability of the deviation should be less than 0.05, so you are tightening things here, you get n equal to 5750. Okay, so n rapidly increases as you would imagine. So this is the Hoeffding's inequality, and this is going to be the starting point for our subsequent discussion. Okay, we saw what the Hoeffding's inequality is in the previous slide, and now the question remains, how do you extend it to the idea of E in and E out? I mean, we spoke of colored marbles, and how do you map that Hoeffding's inequality to E in and E out? This requires a nice little trick, a clever trick, and this is, this is the first of the many interesting logical arguments we are going to make. So let's see how this extends, how the Hoeffding's inequality extends to E in and E out. This was your infinite bin and you drew n marbles, right? Let us say H is any hypothesis. H is any hypothesis from the hypothesis set, and F, as we said, is our target function that we want to get close to. H is any hypothesis, any one hypothesis. We know that each marble is a point in the input space. So you have X, you said that your input space was X and Xi was a point in the input space. And let us assume that since this is an infinite bin, this is a bin of infinite size, let us say that each marble in this bin is going to represent a point from the input space. So each of these is an Xi, right? And this is the entire input space X. Now what we are going to do is we are going to color the marbles in a specific way. Okay. All the marbles where the output of H does not equal the output of the target function F, we are going to color those red. Okay. So the red marbles are the ones where the output of the given hypothesis, output of the chosen hypothesis, does not equal F. H could be any hypothesis. I keep repeating this. And for that hypothesis, if the output of that hypothesis does not match the output of the target function, you color that particular marble red. And remember, these marbles represent points in the input in the input space. So all the points where H did not match F, you colored them red. And all the points where the output of H matched the output of F, you colored them green. Okay. So this is the coloring of marbles that we are going to do. Remember, I said in the earlier slide that the Hoeffding's inequality holds for any ratio of green and red marbles. And therefore, the Hoeffding's inequality would continue to hold if I colored these marbles in a specific way, and that specific way of coloring the marbles depends upon the hypothesis given to me, and this is how I color them. H of x not equal to fx are red, h of x equal to fx are green. Okay. So now with this sort of a coloring, what do we have? We have mu. Mu is now the probability of h of x not being equal to f of x. Okay, and this is indeed Eout. On the entire input space, mu is now Eout. Okay, mu is the probability of h of x not being equal to f of x, right? Which is actually Eout. And this is the probability on all unseen data. That means all the entire input space, right? Nu, on the other hand, is the ratio of points in the sample set where h of x does not equal f of x, and this is indeed our Ein. So on these samples selected, this is your training data that you selected. These were the n points or the n marbles that you selected from this infinite bin, and on this set of n points, the ratio of the red marbles, which is basically the ratio of points where h of x does not equal to f of x, is basically En. So that is your nu, right? So the mu and nu, which basically were the probability and the ratio of the colors, the red colors in the previous slide, are now mapped onto Eout and Ein simply because we decided to color the marbles in this way. And we can do that because, like I said, Hoeffding's inequality applies to all possible ratios. Okay, great. So like I said, this is a neat little trick, and what now happens is this. Your Hoeffding inequality can now be used to correlate Eout and Ein. And just substituting Eout for mu and Ein for nu in the earlier slide, what I get is probability of the absolute difference between Eout and Ein being greater than any given epsilon is less than this quantity, 2 e to the minus 2 epsilon square n. And this applies for any given hypothesis. So if you are given a hypothesis, again, if you are given a hypothesis, you do this kind of coloring of your infinite bin. This becomes your Eout and Ein, and therefore this Hoeffding's inequality now applies for any given hypothesis. This looks great because this is what we set out to do. And I mean, are we now saying that this is simply our delta and we are done? Looks interesting. Not quite, because the earlier slide, like I said, applies for a hypothesis, right? So for any hypothesis in the hypothesis set, this equation applies. We saw that is true. However, what we have in our learning problem is not one hypothesis, but a hypothesis set. Okay, so we have numerous hypotheses in our hypothesis set. And the question, therefore, we need to ask is, how does this bound change when we talk of a hypothesis set instead of a single hypothesis, right? So to repeat, this equation, this Hoeffding's inequality holds for a hypothesis, but when we are given a hypothesis set instead of one hypothesis, how will this bound change? That is now the problem before us. Okay, we are now going to talk about why probability bounds over sets are different from the probability bound on an individual member of the set. Okay, and indeed probability bounds over sets are higher than the probability bound of an individual member of the set, right? So let's see what we have. What we have is that we have a hypothesis set H that had numerous hypotheses in it. And for any one hypothesis of this hypothesis set, we said that this inequality holds, right? So this bound holds for any one hypothesis of the hypothesis set. I'm going to make sure that we understand what event we are talking about. Okay, we are talking about an event here, and the event is the absolute difference between Eout and Ein being greater than a given epsilon. Okay, this is the event that we are talking about. This is the event we are talking about, and it is a bad event. It's a bad event. If Eout differed from Ein by a vast amount, that would be bad. So if Eout minus Ein, the absolute difference was greater than your specified epsilon, you would call that a bad event. And this is actually upper bounding the probability of a bad event, right? And therefore this is a useful bound. So this is our bad event, Eout minus Ein, absolute value greater than epsilon. This is our bad event, and this bad event is for a hypothesis. Now I'm going to make a set of statements one after another, and though these statements will logically explain to you why probability bound over the set is higher. Okay, so let's go over these statements one by one. Okay, the first thing to notice is what we have here is a definitive bound on probability and not a probabilistic bound. So in other words, what we are saying is the probability of this bad event happening. The probability of this bad event happening is definitely not higher than this quantity. Okay, so we are not saying that it is probably going to be less than this quantity. The probability is definitively bounded by this quantity over here. That's the first thing we need to understand. Okay, so this is a definitive bound on the probability of a bad event. Number 2, probability of bad event happening over a set is different from bad event happening to a single member of the set. Okay, because the set has multiple events, has multiple members in it, and therefore there is clearly a difference between a bad event happening over a set vis-a-vis a bad event happening to a single member of that set. Probability of bad event happening over a set is higher than bad event happening to any single member, because over a set, bad event could happen to any member of the set. This is an important line, so you can read it again, right? Probability of bad event happening over a set is higher because when you are talking about a set, the bad event could happen to any one member of the set. Okay? That's the reason why it is higher than bad event happening to any single member. Statement number 4. The bound that we are estimating, the bound is estimated before the final hypothesis is determined, right? Else we would be doing only verification. Now this is again important to understand. When we are trying to find a bound on the probability of a bad event happening over a hypothesis set, we are usually doing that before the final hypothesis is known to us, right? Because if the final hypothesis is already known to us, there is no question of probability and bounds, etc., etc. All you do is you find the Eout, you find the Ein. I mean, you find the Ein based on the training samples you already have, and you find the Eout by looking at the at some test data, right? And then you are only doing verification. There is no question of a probability of a bad event and a bound on it and so on and so forth. You can actually determine what the Ein and Eout are, right? So the bound on the hypothesis set, the bound on the probability of a bad event on the hypothesis set is estimated before you know what your final hypothesis is. And finally, your worst case is the scenario where your final hypothesis could be the one to whom the bad event happened. Okay? So again, when you're talking of a set, the bad event could happen to any member of that set, right? The bad event could happen to any member of that set. And in your worst case, the final hypothesis that you select, which minimizes your Eout, could be that one hypothesis to whom the bad event happened, right? Therefore, the probability bound over a set has to be higher than the probability bound for a single hypothesis. Okay. Now, this is something that, some people still have an issue with. So, I'm going to explain it with an analogy. A high jump contest in a school. Okay. A high jump contest in a school. Let us say there is a school in which the PT, the physical training instructor, decides to conduct a high jump contest among 400 students of that school. Okay, so he puts a bar like this, a high jump bar, and students jump one after another, and there is like a mattress or some sort of a cushion kept on the other side, and students land on that cushion. The probability of student I breaking his arm is, let us say, beta I. Okay. Now, each of these students is going to jump, and I want to sort of think about a bad event, and clearly a student breaking his arm would be a bad event. And I am saying that the probability of a particular student I breaking his arm after he jumps is, let us say, beta of I. Okay. Now, let's say this beta of I was a small number. Okay, let us say 2 in 1,000, 0.002. Okay, a pretty small number. Now, the physical training instructor, the PT instructor who was conducting this contest, had only a passing familiarity with probability theory. So he said that as students come to jump one by one, for each student the probability of him breaking his arm is very small. So let us conduct this event and we can permit that student to jump. Okay, and he conducts this contest amongst 400. He wants to conduct this contest amongst 400 students. Okay, this is his logic. The probability of any student breaking his arm is pretty small. So let us do this contest amongst 400 students. So he takes this plan to the principal of the school. The principal of the school was a lady with immense wisdom. Okay, she was a lady of immense wisdom, and she asked the question. What is the probability of some student breaking his arm? Okay, so she was wise enough to ask the question, what is the probability of some student breaking his arm? Because she didn't want any student to break his arm. And she did the computation, and this computation was really the probability of union of EI, where EI is the event that once the student I breaks his arm, and she wanted to find this probability, right? And this, as you know, the probability of some student breaking his arm is 1 minus the probability that no student breaks his arm, and this is a multiplication, as you know, multiplication of multiple terms. And if you evaluated this, you had to estimate this, and if you evaluated this, you get the answer 55%. Okay, so if the PT instructor went ahead and conducted this exercise, although the probability of a student breaking his arm is extremely tiny, if he ran this contest amongst 400 students, the probability of some student breaking his arm would be 55%. You agree with this, right? This is simply the probability of union of the individual events, each event being that the student I breaks his arm, right? So this is the difference. This is the difference that I am talking about. Now, what is the upper bound on the probability that the best student breaks his arm? So, for example, students, like I said here, they jumped over this bar one by one. And what is the probability that the guy who jumped the highest breaks his arm? What is the upper bound on the probability? What is the worst case scenario? What is the upper bound on the probability that the best student breaks his arm? It is simply the probability that some student breaks his arm, right? Because the upper bound would pertain to the situation that some student, at least one student breaks his arm, and it so happens that that student was the one who jumped the highest, right? So the upper bound on the probability that the best student breaks his arm is actually 55%. Okay. I'm not saying it's probably the case that the best student breaks his arm. I'm not saying that's the case. What I am saying is that if you had to find a definitive upper bound on the probability that the best student breaks his arm, it would be the probability that some student breaks his arm, and unfortunately that one student who broke his arm was the guy who jumped the highest, right? So therefore, the definitive upper bound on the probability over the set of 400 students would have to be 55%. Substantially larger than 0.002, right? So this is what we are talking about. Let's come back to sets. Okay, so let's talk about sets and let's sort of recap something that we all learned in probability theory. The probability of at least one of multiple events happening is the probability of union of events. You know what the union is. You've studied this in probability theory. The union of a number of events is the probability that at least one of those events happens, right? So this is a Venn diagram with events A, B, C and D drawn in 4 different colors, and the union of these events is the area that is covered by at least one of these 4 events, right? The area that is covered by at least one of those 4 events, and the probability of A union B union C union D we know is less than or equal to the summation of the probability of individual events, right? So the area covering the points that lie in at least one of these events is less than or equal to the probability, the summation of the areas of A, B, C and D. We know this. And why is this less than or equal to? If these events are non-intersecting, it would be equal to, and if there is even some intersection between any of the events, it would be less than, right? Because this does not take into account the intersections. So probability of A union B union C union D is always less than or equal to the summation of the individual probabilities, right? Okay, so this is known as the union bound. Okay, this is known as the union bound. We know this from probability theory. And therefore, applying this union bound, the probability of some student breaking his arm, this is what you were interested in. In the last example, we took actual numbers and computed this. But in the general case, the probability of at least one student breaking his arm would be less than or equal to the summation of the probabilities of each student breaking his arm. This is the union bound, and this always holds. Okay, this always holds. Okay. Now let's come back to our hypothesis set. Given the hypothesis set with M hypothesis in it, given a hypothesis that has M hypothesis in it, for each of the M hypotheses, the probability of a bad event is upper bounded in this way. This is the Hoeffding inequality that we saw. This was our bad event, and the upper bound on the probability of a bad event happening for any one of the hypotheses is upper bounded in this way. Okay, and therefore, if I had to apply the union bound to the set of M hypothesis, if I had to apply the union bound to the set of M hypothesis over the hypothesis set, the probability of a bad event happening would be less than or equal to M times this quantity right here, right? Because there are M hypotheses, and this less than or equal to stands because we are applying the union bound. Okay, to repeat, for each of the M hypothesis, this held, and therefore over the union, we want to consider the union over the over the set of M hypothesis. This probability, the probability of a bad event happening, is going to be upper bounded by M times this, just the union bound. Okay. Great. So this is all I'm saying. In our framework that we have been talking about, we had this learning algorithm and the hypothesis set. Given the hypothesis set H, given the hypothesis set H, over the hypothesis set, before you find your final hypothesis, all you can say is that the probability of a bad event happening, the probability of Eout minus En absolute being greater than your given epsilon, is upper bounded by the cardinality of H, which earlier I said was M, by the cardinality or the number of elements of H times this thing that came from Hoeffding's inequality. This is simply the union bound applied to the hypothesis set, right? Now, you could immediately jump at this result and say that this is a laughably useless result, okay? It may be completely useless, but it is accurate. That's all we care about right now. It may be completely useless, but it is accurate. And why could it be useless? I mean, the hypothesis set could have fairly large cardinality, and this quantity could be greater than 1, right? And then you are saying that the probability of something is less than or equal to 1, which makes it completely useless. In fact, the cardinality of the hypothesis set could be infinite, in which case you are saying that the probability of a bad event happening over the hypothesis set is less than or equal to infinity, which you anyway knew before you even started this lecture. So, we are at a place where the bound that we have does not look particularly useful, right? But like I said, although it may not be very useful, as it stands, it is correct. The bound is correct. This is a correct statement. This is a correct statement, right? Okay. Let's proceed further. Union bound for overlapping events. What do we have here? Okay, this was the Venn diagram that we saw. This was the Venn diagram that we saw earlier with events A, B, C and D. And for this Venn diagram, we said that the probability of A union B union C union D is less than or equal to the sum of individual probabilities. This is the union bound. Now, the union bound can be made tighter if there is a significant overlap between the events, okay? Or the union bound as it stands would be a very loose bound if these individual events were highly overlapping, right? Because if they are highly overlapping, the intersections are high, and the intersections are what we ignored when we created the union bound, right? So clearly, this would become extremely loose in scenarios where the events A, B, C, D, etc. have a high overlap amongst themselves, right? So, in other words, if you had this kind of a scenario, instead of less than or equal to, you would say this, right? Because this would be a very, very loose bound, and therefore the probability of A union, B union, C union, D would be significantly less than the summation of the individual probabilities. Okay, let's keep this in mind. Estimating the overlapping can help make the bound tighter. Now, you know that this bound would become more and more loose if there was a level of overlap between the events, and therefore if you can estimate the amount of overlap, perhaps you can do something to tighten the bound. Okay, the bound we saw in the previous slide, which could be so loose as to be completely useless. You can start tightening that bound if you can estimate the overlap between the events that you're talking about. Okay, so let's proceed to estimate the overlap in our events. Great. This brings us to what is known as the Vapnik Chervonenkis bound, or the VC bound. You have seen this name in an earlier lecture, and let's see what this bound is. Now, in an earlier slide, I said that we arrived at this conclusion: probability of a bad event happening over the set is less than or equal to 2 times the cardinality of the hypothesis set multiplied by this term, right? This is where we were 2 slides ago. What are the events that we are talking about? What are the events that we are talking about? We are talking about the events that E out minus E in is greater than or equal to epsilon for each hypothesis, right? For each hypothesis, these are the events. These are actually the bad events. And we are estimating the probability of these bad events for each hypothesis. Okay. These events we claim have a high overlap. Okay, these events have a high overlap which needs to be estimated to make this bound useful. This bound may not be useful because the cardinality of H could be infinite, let alone large. And therefore, if this bound has to be made useful over a set, we have to estimate the overlap of these events. Okay, the events being absolute value of E out minus E in greater than your epsilon, right? Now, I want you to pause the video here for a minute and think about what we have studied in the past that gives you an indication of the overlap between these events. Okay, you can pause the video over here for a moment and think. Have we looked at something in the previous lectures that in any way points to the overlap between these events? I'll proceed. Estimating the overlap is a key idea in getting a better bound or getting the Vapnik Chervonenkis bound. And I'm going to put the final result on screen here. It says that the probability of E out minus E in being greater than epsilon is upper bounded by 4 times growth function of 2n e to the power epsilon square n over 8. Okay, so instead of the cardinality of H, once you estimate the overlaps of these events, instead of the cardinality of H, you end up with the growth function of H. Okay, therefore this is a very, very important result, and it is possibly the most important result in the theory of learning, because now it gives you a more useful bound, a more meaningful bound on the probability of a bad event happening over the entire set. Okay, you may have to roll back a lecture to find out what this growth function is. We have covered it in detail, and the reason I sort of covered it earlier was so that you knew why it fits in over here. Okay, so this is the result that is a really important result, and what it does is that it gives us a meaningful bound on the probability of a bad event happening over the entire set. Of course, this result needs proof. Okay, and the proof is runs into several pages. Like I've said earlier, we will cover all the key proofs, or at least give pointers to those proofs in a separate lecture. Here, what I want to do is, simply because this is such an important result, I want to go ahead and give you some insight into the proof, not give you the actual proof itself, but basically tell you why something like this happens, right? I mean, also there are certain curious things going on over here. You would have expected this to be the growth function of n, but it's mh of 2n, and then there are some constants that have changed here and in the exponent as well. So I'll just give you a broad sense for the proof rather than giving you the entire proof right now. I'll give you pointers to the full proof in the separate lecture that we have. But let's spend a slide, given the importance of this result, let's spend a slide trying to understand this result. Insights into the proof. Okay, we made this transition from this result, which we knew, to the VC bound that looks like this. And as we said, a few things have changed. Instead of the cardinality of the hypothesis set, we now have the growth function, which is the biggest change that has happened and the most seminal and important change that has happened. And of course, certain constants have changed here and in the exponent as well, right? So let's focus on this first. This has happened because we estimated the overlap, like we said. So what is it about the overlap that we are talking about? We said E out minus E in greater than epsilon are the events, and we said that those are highly overlapping, right? Now, E in we know has a high overlap, right? And there are mh of n uniques for n point as seen in the definition of the growth function. We saw the growth function in an earlier lecture, and we said that the growth function has to do with the specific n points that have been given to us. And since E in deals with those specific n points, we already saw that E in has overlap amongst different hypotheses, right, of the hypothesis set. In other words, you can choose a number of hypotheses and all of them would give the same E in. We saw that earlier. And the number of unique E ins that you would get for n points are defined by this growth function, which counts the dichotomies and so on and so forth, mh of n. You can roll back to a previous lecture and see this. But what about E out? I mean, we are talking about E out minus E in over here. So what about E out? I mean, E in we know has a high overlap. We saw that. But what about E out? Consider the bin that we saw earlier a few slides ago. And what we are now claiming is that E out can be estimated by drawing another n marbles. So you drew n marbles for estimating E in. Right, your E in was computed on the basis of your n training samples. We say that E out can also be estimated or approximated by drawing another n marbles. Okay, and that is broadly the reason why you get mh of 2n over here, and epsilon gets tightened to epsilon over 4 as you go through the proof. Like I said, I'm not trying to prove this result here. I'm trying to give you a broad sense of why the cardinality of h gets replaced by the growth function whose argument is 2n instead of n. Okay, so this is the reason why, broadly the reason why you end up with this VC bound. Okay, we now come to generalization and learning. Okay, this is an important result. I cannot state its importance adequately, but this result is going to show us why generalization or learning becomes possible. Right? So here we are sitting now with the probability over the set, right? The probability of the bad event over the set being upper bounded by this quantity right here on the RHS. Here is what we have studied earlier. We have seen that if mh of n, if the growth function has a breakpoint, mh of n grows slower than a polynomial of degree d, where d is the VC dimension. Okay, this is also called the Sauer's lemma, and when we saw this in an earlier lecture, we said that this needs proof, and that proof will follow in a subsequent lecture dedicated to proofs, right? But we saw this earlier. If mh of n has a breakpoint, if your growth function has a breakpoint, it grows slower than a polynomial beyond that n, and that polynomial happens to be of degree d, where d is the VC dimension. We saw what the VC dimension is earlier. And therefore we can say that the probability of a bad event over a set is upper bounded by 4 times a polynomial of degree d times this quantity, right? So I'm replacing this with this because this is less than this, and therefore this inequality would continue to hold, right? So what we have now is this. Very important. This bound is going to decrease with increasing n, right? This bound is going to decrease with increasing n. In fact, you can make it arbitrarily small as you like, by increasing n. Why is it going to decrease with increasing n? Because this is only a polynomial of degree d, whereas this n here is in the exponent, and we all know that a negative exponent will completely kill any polynomial, right? An exponent grows faster than any polynomial, you know that. So a negative exponent will decimate, will kill the growth of any polynomial eventually as you increase n, right? So what we are saying now is that this is a very useful result. This is essentially what we always needed. This is what we set out to find, and we have arrived at this conclusion that the probability of a bad event happening over the hypothesis set is upper bounded by a quantity which can become arbitrarily small as n increases, right? As n increases. So I'll restate this result. The probability of Eout minus E in mod, the modulus, that means the probability of Eout differing from En by larger than any given epsilon, can be made smaller and smaller by increasing n. Okay, which means Eout, you can make sure that Eout is as close to En as possible, and that is indeed generalization, right? That is indeed generalization, and therefore learning is possible. Okay, now when is learning not possible? We saw that pathological case where this had no breakpoint. I mean, we were talking about the hypothesis set of all convex functions. In that case, this would not be possible, and therefore learning would not be possible if your hypothesis set contained all convex figures, right? So for any other hypothesis set that has a breakpoint, learning is possible. Again, I mean, this bears repeating. Why is there a probability? Why are we still talking in terms of probability? What is the random variable? We said this, it is the data set used for training, right? I mean, if you get a particularly bad data set, you could possibly end up in a situation where this probability, where this bad event happens, but the probability of that bad event will go to 0 as n increases. Okay, so couple of other things. Here we are again looking at the equation that we had earlier, and we are going to call this delta. This term on the right, we are going to call it delta. Remember the delta of our first few slides where we said that you wanted this to be less than delta. This is our delta, and like I said, delta depends upon epsilon, delta depends upon n, and it also depends on the hypothesis set that you choose. And again, delta can be made as small as possible by increasing n, right? So this sort of closes the loop. It closes the loop with our earlier slides where we set out to do something like this. Now, if delta is this, I can simply rearrange terms and write epsilon in terms of delta, right? I can write epsilon in terms of delta. So delta is related to epsilon, epsilon is therefore related to delta. There are a few things to notice. As epsilon decreases, n has to be increased to maintain the same value of delta. And similarly, as delta decreases, n has to be increased to maintain the same value of epsilon. Okay. So as you go to smaller and as you dictate smaller values of epsilon and delta, you would have to increase n to meet those requirements. But you can always get an n that meets the requirements of the epsilon and delta that you have specified. Very important. For more complex hypothesis sets, the ability to generalize is lower. You need a larger n. Let's understand this. Now, let me remove this. Now, like I said, this is your delta, right? This is your delta, and your objective is to minimize delta as much as possible. And your delta contains this term over here, which is the growth function. As you know, more and more complex hypothesis sets have higher and higher growth function values for the same n, right? So more complex the hypothesis set, more dichotomies it can create on a given number of points, and therefore the value of MH for a certain number of points is higher for more complex hypothesis. Now, if this increases, in order to maintain the value of delta, you have to keep increasing n, right? You have to keep increasing n to compensate for any increase in the growth function if you want to maintain the constant delta, right? So effectively what we are saying, for more complex hypothesis sets, the ability to generalize is lower. Essentially, you require larger and larger n's. You require larger and larger training data if you choose more complex hypothesis sets. This is again fairly intuitive, but there is a difference between something being intuitive and something being actually proved, and what we have proved right now is what your intuition probably suggested in the first place. While this result is important in its own right, let us see some of the practical implications of the VC bound. Okay. Now, the VC bound told us that probability of the absolute difference between E out and E in exceeding a given epsilon is less than delta, where delta is this, right? So this is what the VC bound told us. Now, normally the way it would go in practice is that you would like to specify a delta and an epsilon, and you want an estimate of n for a particular hypothesis set. Okay. So you would say that I want my E in and E out to be within, let us say, 0.05 of each other. So relatively close to each other 98% of the time, right? That is what you would specify, and you would ask the question, what is my required n for a hypothesis set which has a particular VC dimension? That is the question you would ask, right? So before we jump into answering that question, let us first understand one thing, okay? And that thing is the relationship of the VC dimension to the required n. Okay. Based on this relationship where delta equal to 4 times mh2n, etc., and you know that this is upper bounded by a polynomial whose highest order is dVC, a polynomial essentially of order equal to VC dimension. What can you say off the bat as far as the relationship between n and dVC is concerned? I mean, what you can immediately say is that you do not want to choose a hypothesis set that is more complicated than needs to be. Okay, so you are better off avoiding a hypothesis set that is more complicated, or which has a which has a higher VC dimension, or which has a strongly growing growth function. You are better off avoiding that kind of a hypothesis set unless you need it, right? So use a hypothesis set that is adequate for your needs, but no more complicated than that, right? So Why is that the case? That is the case because, as we said earlier, if you have a higher VC dimension, if you have a growth function that grows more strongly, then the n required to nullify the effect of that growth function would be higher. And you essentially would require larger number of points in your training data, right? So anyway, coming to this question, this is typically this kind of question you would ask. You would specify an epsilon and delta, and then you would ask the question, what is the required n for my hypothesis set? And you would probably know the VC dimension of your hypothesis set. Okay. So this is the question we are asking. Given certain values of delta and epsilon, how does n depend on dVC? Let's go over this exercise. We are going to plot a few curves. Okay. We know that delta is equal to this. Okay. And we know that this growth function is upper bounded by a polynomial of degree d, where d is the VC dimension of this hypothesis set. So let us consider, for example, just the highest term in that polynomial, right? And let us approximate delta is equal to 4 times n to the power d e to the epsilon square n upon 8. Okay, so let's approximate this growth function by its highest term, because and why is this an approximation? It's an approximation, it's an okay approximation, because as n increases, the highest order term will dominate all other terms. So that's the reason why we have taken the highest order term over here. What if we plot just n to the power d multiplied by e to the minus n versus n for various d's? I mean, for one d, this is for d equal to 10. I have plotted this graph, and this is n to the power d e to the power minus n plotted against n. So the x-axis has n, y-axis has this quantity is on the y-axis, and this particular plot has been plotted for d equal to 10. Okay. Now, usually you would specify small values of epsilon and delta, which means that you would probably want to operate in this region. Okay, in this region. Now, this graph itself, like I said, has the behavior that you would expect. Initially, this graph climbs up because n to the d is the dominating term, but very soon e to the minus n starts killing it, right? And therefore the graph goes down and it goes to 0. I mean, you can make this term as small as you like by increasing n. So you would typically specify small values of epsilon and delta, and therefore you would probably be operating in this range. If you specified even smaller values, you would be operating in this range, and so on and so forth. So if I were to zoom in on this region for various d's, what would I get? Let's plot that. Okay, let's understand what this plot is. This is a plot of n to the power d multiplied by e to minus n for various values of d, with x-axis being n. Okay, and I have taken this snapshot in a region of interest for values of epsilon and delta. Okay, so you would typically say epsilon is 0.005, delta is 0.002, whatever. I mean, over a broad range of values that are interesting for delta and epsilon, this is the nature of the graph of n to the power d e to the minus n versus n. Okay. Now, if you considered a constant delta, you would see that there is a fairly linear behavior with respect to d of this graph. Okay, so let us say if this was the delta that you were interested in, right? These graphs cross this line at relatively regular intervals, right? So as n increases, this is the nature of the graphs, and these graphs cross that that line that I have drawn as at fairly regular intervals. And this can give us a rule of thumb. And the rule of thumb says that for a wide range of relevant values of epsilon and delta, it's a good idea to select n higher than 10 times the VC dimension. Okay, this is a very important rule of thumb. Very important rule of thumb. It says that for relevant values of epsilon and delta, by relevant I mean quantities that are small enough and that are typically used in practice, you should select the training samples, the number of training samples that you pick at random should be higher than 10 times the VC dimension of your hypothesis set. Okay, so if you have a more complicated hypothesis set, if you have a hypothesis set that has a higher VC dimension, you would need more training samples. Okay, and this is a rule of thumb that governs or that tells you how many samples you need to take at a minimum if you are looking at particular values of epsilon and delta, right? So this is an extremely important rule of thumb, and it's because it tells you what you need. It tells you how many training samples you need to work with. Okay. I want to draw your attention to something that is important and which some of you may have already noticed by now. Okay, and this observation has to do with bound versus actual. Okay, so what is the observation I am talking about? Let's look at what we have here, right? Let's look at what we have here. We have this equation that says that probability of E out minus E in exceeding epsilon is less than delta. So delta is basically an upper bound on the probability, right? Now it could well happen that in a particular case you had a high upper bound, okay, and the difference between E out and E in was very small. Okay, the difference between E out and E in was very small. Whereas in another situation, you had a tighter bound, a smaller delta, let's say delta 2, but the difference between E out and E in was larger, right? So this is a bound. This is a bound. Let us say you had a case where the bound was delta 1. Delta 1 was relatively high. I am saying that you could have E out and E in very close to each other and the difference between E out and E in was small. And in another case, your bound delta 2 was small. That means the bound was tight. But E out minus E in, this quantity was larger than what it was in this case. Now, this is perfectly mathematically compliant with this bound, right? I mean, because this is less than delta 1, this is less than delta 2, but it turns out that the actual values are skewed in the sense when delta 2 was small, E out minus E in was larger than in the case where delta 1 was large, right? Think about it, you will see what I'm trying to say, because after all delta 1 and delta 2 are just the bounds. The actual values can still look like this. The practical observation of people who have worked in this area suggests that the actual values move in tandem with the bounds. So if your bound was tighter, you will observe that E out minus E in is likely to be closer to each other, and if your bound was looser, your bound was more generous. What I mean by looser is it was more generous. Your E out and minus E in would be that much larger, right? So higher bounds reflect in a greater difference between E out and E in vis-a-vis tighter bounds where E out minus E in is likely to be smaller. So the actual values of difference between E out and E in move in tandem with the bounds, and this is simply an observation in practice of people who work in this area. Okay. I want to give a definition of what is a PC learnable problem. You will frequently see this definition in literature, and because it is relevant to what we are covering right now, I want to make sure that we cover that definition. It relates to exactly what we have been doing right now, but let me give you the definition as it appears in literature. Okay. A class of target functions f, okay, a class of target functions f is said to be PC learnable if for every target function in f, any small error epsilon given to us and any confidence level delta given to us, there exists a learning algorithm A that can find a hypothesis G such that probability of Eout being higher than epsilon is less than delta, with a complexity that is a polynomial function of 1 over epsilon, 1 over delta, and the VC dimension of the hypothesis set. Okay, it's quite a long definition, but if you read it once again, you can easily correlate it to what we have been talking about so far. All that this is saying is that a class of target functions f is said to be PAC learnable, probably approximately correct learnable. This is a definition. If for every target function in f, so no matter what target function you choose in that class of target functions, if you are given a small epsilon and small delta, there is a learning algorithm A which can identify a hypothesis G out of your hypothesis set such that the probability of Eout being higher than epsilon is less than delta. So, of course, what we are saying is the hypothesis set is such that you can find a hypothesis where E in is 0, right? So, you have a hypothesis set where E in can be made to be 0. Okay, and furthermore, therefore, if E in becomes 0, your PAC equation that you saw earlier becomes this, right? And you can essentially find, there exists a learning algorithm A which can ensure this with a complexity that is a polynomial function of 1 upon epsilon, 1 upon delta, and the VC dimension. Now, earlier we saw it was polynomial in the VC dimension. We saw that earlier, and we said that we could find a hypothesis set for any value of epsilon and delta, and that is what this essentially says. Okay, so that is what this definition is. PAC learnable. A problem is PAC learnable. What is PAC learnable? The problem is PAC learnable, and the problem means the class of target functions that you are trying to approximate, right? So this is the definition of the PAC learnable problem. It maps exactly to what we saw earlier, but this is the formal definition, and that's the reason I thought I should share it over here. Polynomial function. So if epsilon is small, delta is small, you cannot take forever to come up with this hypothesis. You have to come up with the correct hypothesis in polynomial time. In polynomial time and in polynomial effort. Effort meaning computational effort. Okay, let's move on. I have another definition for you. The generalization bound. The generalization bound, again related to what we have been doing so far. We have said that we have looked at this equation on many slides so far, where delta is equal to this quantity. Okay, and therefore what we can say, if we flipped this around, probability less than delta, if you flip this around, what you can say is with probability higher than 1 minus delta, where delta is a small number. So now we are saying with probability equal to 0.99 or 0.999 and so on, with increasing probability, probability greater than 1 minus delta, you can say that the absolute difference between E out and E in is less than a quantity, that is a function of your n, your VC dimension, and the delta that was specified, right? Again, I don't need to repeat this again, but n obviously is available over here, and we know that this is upper bounded by a polynomial of order equal to dvc, right? So this is what we have. And now E out and E in are both positive numbers. They are both less than 1. And in practice, you would typically always see that E out is going to be higher than E in. And therefore, we can write it in this way, right? With a probability greater than 1 minus delta, with a higher and higher probability approaching 1, no matter what delta you specify, your out of sample error is going to be upper bounded by E in plus this quantity, which can be made smaller and smaller with increasing n. This is also known as the generalization bound. It is called the generalization bound because you remember the definition of generalization. Generalization means how well a hypothesis performs on out of sample data compared to in sample data. So this is your in sample error, this is your out of sample error, and you know that your out of sample error is going to be bounded in this manner. This is exactly what we've set out to accomplish at the beginning of this lecture. We wanted to establish a relationship that said that E out was less than E in plus perhaps a quantity that we could get a handle on. We have actually done that. We understand what this quantity is, and for hypothesis sets that have a finite VC dimension, we know that this term, this additional term omega, can be made as small as you like with increasing n. This is known as the generalization bound, and this is going to be useful for us later when we talk about a number of things such as regularization and so on and so forth. Okay, so this is the generalization bound, this is the definition, and this definition is going to stay with us. Great. So I think we've accomplished what we set out to do in the first place at the beginning of this lecture, and therefore it is time to summarize. Summary. We began a couple of lectures ago with the following promise, right? We said that there were two distinct standalone theories in the theory of under the broad umbrella of theory of learning, and one of them was the PAC, or the probably approximately correct theory. And in this theory, we promised ourselves that we would demonstrate that E out is less than E in plus a quantity with a probability higher than 1 minus delta. We said this is what we would show, and we said that our journey towards this goal would take us through concepts like the Hoeffding inequality, the growth function, shattering, VC dimension, finally ending with the generalization bound. That is exactly what we have done in the last couple of lectures, including this one. And we decided to take a slightly different path where we looked at these three ideas first. And hopefully you now agree with me that that was a good idea, right? So hopefully you agree with me that that was a good idea, because it helped us quickly relate those to the discussion that we had today. So what was the summary of today's discussion? Let's see. We began with the Hoeffding's inequality. And with a clever trick of coloring those marbles in the bin, we came up with the result that the probability of the absolute difference between Eout and Ein being higher than epsilon for a given epsilon would be less than 2 to the power E square epsilon to the power 2 multiplied by n. So this was a direct fallout of the Hoeffding's inequality. We then argued that the bound over a set would be necessarily different and necessarily higher than the bound on one hypothesis. The Hoeffding's inequality gave us the bound for a hypothesis, and we came up with the bound over an entire set that was higher than the bound for a single hypothesis. We took an example to see why that was the case, but this is the bound that we got. This is the bound that we got, where over here we ended up with the cardinality of our hypothesis set. This was a result of the union bound. We then proceeded to tighten this bound by noticing the overlap in the events represented by the different hypotheses in our hypothesis set. And this was a key result of today's lecture, today's session, where we said that the probability of the absolute difference between Eout and Ein being higher than epsilon no longer had this cardinality of h, which could be infinite, but it had this term, the growth function, which we saw last time in the earlier lecture. And this was very useful because we know that the growth function grows only as fast as a polynomial of order equal to the VC dimension of the hypothesis set. And therefore, we ended up with this generalization bound. Which told us that E out was going to be less than E in plus this quantity, and this, as long as your VC dimension of the hypothesis set was finite, this quantity would go to 0 with increasing n, which meant that your E out could be made as close to E in as possible, which means generalization is possible, which means learning is possible. Learning in the sense, if your E out becomes closer and closer to E in, it means generalization is possible, it means learning is possible. You can pick a hypothesis set which gives you smaller and smaller E-ins, and as long as the VC dimension of that hypothesis set is not infinite, your E-out can also be made smaller and smaller, right? So this was the summary, this was the conclusion of today's lecture. It's been a good one. I hope you enjoyed it. I hope you liked the various theoretical concepts that we studied along the way. That's it for today. Goodbye.